Hi everyone, I'm back with another topic that's related to Python or machine learning, and in this case I'm going to focus on defining the terms mean absolute error and mean squared error. You probably know what they are, but let's just put them in the context of machine learning, how they can be good metrics, and also how they can be used as good loss functions. And as we're discussing about these, we'll also just have a quick look at Huber loss because it is kind of related to mean absolute error and mean squared error. And the first part of this video is going to be just going through a few slides so we make sure that we understand exactly what the terms are. And the second part of this is going through a little bit of code. So we basically support whatever we learn via these presentation using the code, using our experiment. So I'm going to share the code with you. You have something tangible in your hand after watching this video so you can play with it and then increase your understanding if you still are confused about this topic. So let's go ahead and jump in by first understanding the terms of mean absolute, mean squared error. What do we mean by using that in a loss function? So let's say we have some data. And of course, we are looking at a regression type of analysis, but just let's say the dots here are the data points that we are trying to fit. And we are trying to represent, what do we mean by fit? We are trying to represent these data points using some sort of a function that we can use in future to predict our values. So once I fit the straight line to this data points, in future, when I'm doing my experiments, if I get a value of 0.2, I can refer back to this function. I can say, okay, this is my model. My input is 0.2. Show me what the output is, and it gives us an output of around 0.2 something. And that's exactly what machine learning is, right? So show me what the value is. My inputs are dates, and my output is the stock value. And just predict what the value of, say, a certain stock is going to be tomorrow. So tomorrow would be right here. Okay, tomorrow the value is right there. Of course, it's not going to be linear in that case. It's going to be some sort of a fluctuation. Just giving you a quick example so you can kind of relate to that. I'm pretty sure most of you know that anyway. Now, let's say this is the model. And is this a very good fit to the data points that we have? Well, if you just look at this specific data point, then you can say that is not a good fit because you see how far the data point is from what the model is telling us where it should be. This data point and this one are excellent. So if the machine learning algorithm is trying to optimize this, then it moves the line towards this data point. But then if that happens, then the line is probably moving away from some of the other data points. So it all comes down to a good balance between all the data points that I have in here. Now, what happens if there is a data point right here? A complete outlier. So at 0.4, instead of getting a value of around 0.3-ish, what if I get a value of 0.15 in my experiment or whatever I'm trying to do here? That is obviously an outlier, right? Then do you want to give a lot of weight to that outlier, or do you not want to give some weight to that outlier? Why am I mentioning about that? Because that defines what type of loss function you would like to use, right? Mean squared error is good for one thing, mean absolute error is good for something else. So it depends on whether you want to give some weightage to the outliers or you don't want to. And we'll understand that in a minute because it's pretty intuitive actually. And bulk of this presentation is based on intuition. So I hope it makes sense to you guys. So how do we quantify the error? How far is this from the line? It's pretty straightforward. Like you take your coordinates. Okay, this one is for a given value of x2. I'm getting a value of 0.4 something. That is my y2. And ideally, my actual data point is at x1 and y1, right? So at that data point, my actual value is 0.35. So the error in this case is 0.35 minus 0.45. So I get like negative 0 point, right? So that is a negative value. So now take it to this one. This will be a positive value of 0.01 or something. When you add all the errors, if this is negative, that's positive, that's negative, there's a good chance that they all add up to something like 0. Then you would think, wow, your model is amazing. That's why you definitely do not add everything as is. You take the minus away and only look at the magnitude. If you just say, okay, this y1 minus y2 is negative 0.1, so drop the negative and just use 0.1. So 0.1 is the error right there. That's called absolute error. So you take an absolute error right there, you take an absolute error here, same thing, and you add all of them and divide by total number of points, which means you're taking an average. That's called mean absolute error. That is one metric. Okay, so that is one thing. Keep in mind. Mean squared error. It's a good metric. I should have said MAE and MSE are good metrics to evaluate the accuracy of model. Mean squared error is, as the name suggests, you take y2 minus y1, just the error, but instead of just taking the absolute value, you're squaring it. And square takes care of the negative sign anyway. So you're squaring it and then you're adding all and dividing by total number. So basically you're averaging it, and that's exactly the equation for mean squared error. You do y2 minus y1 squared and do exactly the same here, which means you add all of those and divide by total number. So that's your mean squared error. When you use this as a metric, that absolutely tells you how good is your model in relation to your data points right there. Is it good? Is it bad? Now, oftentimes people ask me a question, I got a mean absolute error of, I don't know, 20 and mean squared error of 400. Is that good? I have no clue. Look at your data points. What's the magnitude of your data points? And if I say, okay, I have a accuracy of, plus or minus 1 mile in terms of estimating the distance from here to my office, that's not good because my office is 3 miles away. And plus or minus 1 mile is a lot when you compare it to 3 miles. But then from here to the moon distance, if I have an accuracy of like 1 mile, that's freaking amazing. Yeah. So the magnitude of your mean squared error and mean absolute error, what it is, depends on what values you're dealing with and in what context are you talking about. Okay. So, but that is just using it as a metric. Now, if you use this as a loss function, what does the machine learning algorithm do? All it does is it minimizes this loss function. It says, okay, now the value for mean squared error is 400. Now let me adjust the weights and calculate the value again for the data that you supplied for training. And if it is 390, good, we are going in the right direction. Update the weights again, go back. Now if it goes to 420, I'm like, wow, that's the wrong direction. Let's change it back to something else in the right direction. And that's the job of a machine learning algorithm. And that's a different topic. Look into gradient descent and how deep learning actually works, or even regular machine learning. But the goal for any machine learning or automated type of defining or setting a model, for fitting a model to your data, the goal is oftentimes minimizing a loss function. And quite often the loss functions are mean absolute and mean squared error. Of course, you have other loss function, fancy loss functions like focal loss and all types of cross entropy loss and so on. So let's focus on this topic. So with that information, let's go to the actual definitions. We already saw that mean absolute error is 1 over n times summation of y2 minus y1. That's it. This is just a magnitude of y2 minus y1. So we already looked at that. I mean, it's take the absolute value, add everything, and average it. That is mean absolute error. It's also referred to as L1 loss. And when is that useful? It's less biased for large errors and outliers. Yeah. So if you have outliers, then this one is less biased. Park that topic. I'll tell you what that means. But for now, this is less biased for large if you have outliers. Mean squared error, we just looked at the equation. It's y2 minus y1 whole squared, and add all of them and average it. And this is often referred to as L2 loss. So you have L1 loss and L2 loss. And this one is biased for large errors and outliers, meaning if you care about outliers, think about mean squared error. If you don't care about outliers, if you don't want to care about outliers, think about mean absolute error. And oftentimes people also look at root mean squared error primarily as a metric when you're looking at the quality of your data. Then this is basically take the mean squared error and put a square root to it. So whatever goes with mean squared error, it goes with root mean squared error. So now let's look at some data. So let's say these are the actual numbers that I got from some experiment. and I'm fitting a model to it. Or think of this actual as the training data that you provide. And the predicted, of course, is the prediction from the machine learning model. So you are comparing how good this is with that. And if you just take an error like this, minus that, predicted minus actual, you get negative 14 right there. And an absolute error means you drop the sign and you just make it a positive number. You take the average of it, that is the mean absolute error. And in this example, I'm getting 19.2 as the mean absolute error. I don't have any outliers. We'll do that experiment when we get to our coding part in the next half of this tutorial. So squared error is basically, now you have an absolute error. You just square it. So you get these. Go ahead and add them and average them. That is your mean squared error. Root mean squared error is just a square root of this. And usually the root mean squared error and this one, I mean, you may find that sometimes they're comparable, sometimes they're different. Again, it completely depends on whether you have outliers or not. Yeah, I'll show the data later on when we get to the code part that if you add just one outlier, that value goes crazy. That's why squared error is good loss function if you have if you care about outliers, but it's not if you really do want to ignore the outliers. Quick overview right there. Yeah, and why is it good for outliers? Because if you look at this loss function, this is again mean squared error. And if you plot the equation, like this is just square, right? If you plot that equation, this is basically a square for negative numbers. Of course, it goes at the square of it, and it's always a positive value because it's square, and also symmetrically goes up in the positive side right there. Now, if you just look at, okay, if an outlier is right here, then that is how far it is away from true, which means on the y-axis there is a lot of difference between where the model tells me it should be and where it actually is. Yeah, so if you think of this as a loss function, so if on the y-axis you say that is the weight or the importance that it gives to the outlier, then if the outlier is right here, it actually gives a lot of weight or a lot of importance to that outlier right there. So this is why, and if what happens if your x, like here x is only like going 2.5 right there, right? So what happens if you just go from 5 to 10, like this much of error, again an outlier, let's say, then the weight goes as a square function, right? So weight goes all the way over there, so it gives more weight to these type of outliers right there. So in summary, if outliers are important to you, if you want to include them, then mean squared error or L2 loss is good. If not, L1 loss is pretty good. Now let's look at mean absolute error. Mean absolute error is basically, as you can see here, this is how you can actually plot this. We'll do the plotting in Python in a minute, but it does not put too much weight on outliers because it's a linear function. It's not an exponential or a square function right there. And the loss right here provides a good measure of how well the model is actually performing. If you look at, let's zoom in, right? I mean, I'm just going to zoom in right around that area. And if you look at the same error as before, like when you just say, okay, my data point is that much away, and the weight that mean squared error gives is all the way up here, and the weight that the mean absolute error gives is pretty much down here, so not much weight. So most of things are almost equally weighted or given equal importance. Okay, so with that information, in fact, yeah, the question I pose here is, what if you want something in between? I mean, these are two extremes. This one is like too much weight for outliers. This one is not enough weight for outliers. What if I want to give a little bit of weight, something in between these two? This is exactly where Huber loss function falls in. Huber loss function given by this equation, all it does is, hey, if the value falls below certain delta is something that we can control. As a user, we can define that, hey, this is my delta, then it is linear, then it is, the mean absolute error, and if it is above, it is like very much close to the mean squared error. So by defining the delta, you can say whether you want to be very close to, I mean, I believe if delta equals to 0, this function becomes same as, if delta equals to 0, this one is gone, right? So this is all delta. It's just this, in which case it's going to be just mean, is that mean squared error? Yeah. So mean absolute error, sorry, for y. We'll get to the code and then everything makes sense. So all Huber is it's just got this delta as like some sort of a threshold that controls where it falls in between your blue line, which is mean absolute error, and red line, which is mean squared error. So if I increase delta from 1.5 to, for example, 4, you see how it's getting closer and closer to mean squared error. So the smaller delta, the more close it is to mean absolute error. Okay, that is the summary there. Well, in fact, let me summarize whatever I just mentioned. Use MSE if outliers are important as a loss function. Use mean absolute error if outliers are not important, and use Huber function if you would like to have a control in terms of how much weight you want to give to these outliers. Now let's jump into our Python exercise. It's going to be pretty quick, I promise, and I'll share the code so you can play with it yourself. Okay, so we don't need anything special. All we need is NumPy and possibly like scikit-learn if you want to learn about this. But let's just jump in. So with NumPy, I'm going to create some, I'm not sure where I'm using, to calculate the square and some math operations. So I'm going to go ahead and import the NumPy library, and I am defining a list for true and predicted. These are exactly the numbers I showed you in the presentation. So this is the true values or training values, and the predicted is what the model is telling me we are getting. So this is true, this is predicted. So with this, let's go ahead and define our mean absolute error. One way to define that is by just using your NumPy and converting your lists into NumPy arrays, and go ahead and calculate the mean. Of course, NumPy provides a great way of, easy way of calculating the mean. Otherwise, you have to use like for loops to add all of these and divide if you want to handle them as lists. None of us want to do that. So I'm defining a function right there where it takes in a true value and the predictions, like true and predicted right there. And it is going to, I'm defining what my true is, what my predictions is, and I'm converting them into NumPy arrays. And all I'm trying to do here is just true minus the predictions, right? Y2 minus Y1, and take absolute. That's it. That's all I'm trying to do. Absolute Y2 minus Y1. So with that data, let's go ahead and run this function and go ahead and print it. And you can see we get a value of 19.2. Okay, of course, that's exactly what I showed you as part of the presentation. Now, you don't have to code everything from scratch. There are many libraries with built-in mean absolute error. Scikit-learn has it. I know TensorFlow has it. Although TensorFlow, it returns a tensor, so you need to do np.array, I believe, like convert that tensor into an array so you can get the results. But many packages offer you mean absolute error. Scikit-learn is the easiest one, so let's go ahead and use that. So from scikit-learn.metrics, go ahead and import mean absolute error, and let me just print out the mean absolute error calculated between true and the predicted values. It's as easy as that, just a single line, right? 19.2. There's no reason why we should get different values using the pre-built function versus our own functions. So let's do the same with mean squared error. Mean squared error is you're subtracting true and predicted, and you're squaring it. And once you square that, you take the mean of it. That's it. So it's basically a single line, even if you code it yourself. So let's go ahead and do that, and let's print mean squared error. We get a value of 380.4. Again, you can do exactly the same by importing a standard library from scikit-metrics, for example, and do exactly the same thing, and we should hopefully get pretty much the same number. Okay, so you can, the reason I wrote this here is to make sure that you see what mean squared error is. As the name suggests, as the formula that we saw earlier, it's true minus predicted, and then square it, and then mean it, or average it. Okay, so far so good. Let's take exactly the same data, except change one data point instead of 234. So here, my true value is 234. My predicted value is 248, right? True 285, predicted 310. So this is the difference between the true and the predicted. So all I did was copy these two and change 248 to 450. Now that's an outlier. That's quite far away from the actual predicted value in relation to these values right there. So if we do that, how do our mean absolute error and mean squared error looks like? So for that, remember these two. Earlier we got 19.2 and 380.4. So now let's run these one more time. And now we got 39.4 instead of 19.4, 19.2. Okay, not bad, not that far away. But for mean squared error, we got 5,000. That kind of tells me, yeah, of course, there is an outlier or something funny happening with a few data sets in my data. So you can see how this actually grows at a square relationship along with your input data. Okay, so hopefully you learned one thing right there. Now let us go ahead and use these MAE and MSE, understand these as loss functions. So for that, I just want to do a few plots that I showed you as part of the presentation. So one, let's just create data points between, let's create data points between -100 to 100 in steps of 1. And our y, mean absolute error, I'm just taking these values and just getting absolute value so we can plot it. That's what mean absolute is. And if you plot it, you can see how that absolute value is. So we have numbers going from -100 to 100 in steps of 1. And my absolute value is basically just taking whatever that number is and removing the negative sign. So you get nice V-shaped plot right there. Very similar when you do mean squared error. It's nothing but you have your input and you're squaring it. It's proportional to that. So I just want to show you in comparison how it looks like. And we saw this as part of the presentation. So that's how your square goes in relation to your linear right there. Okay, now let's add Huber. Huber is in between the mean squared and in between these two, right? So let's test it out for two different deltas, 1.5 and 4. And mean squared error Huber is 0.5 times x squared. Again, going back to the formula of what Huber is. And the mean absolute error for Huber, it has the delta value, right? So if the delta value is basically 0, it converges towards being a mean squared error. Otherwise, it converges towards being a mean absolute error. So that's, I believe, no, that's exactly the opposite, because when we define the Huber, you actually define, okay, if it's less than certain delta, use something, and if it's greater than that, use something else. So this is the formula that we have actually not come up with, have written from what we saw earlier. And if you run these and if you go ahead and plot, you can clearly see for mean absolute, for a delta of 1.5, it's closer to the mean absolute error. And for delta of 4, it's actually pretty close to this mean squared error right there. Okay, so that is the end of it. And I'm going to, since I'm going to share the file with you, I have included the loss functions. If you want to use this as loss functions, remember in Keras, like TensorFlow Keras, you can actually define external loss functions yourself. Of course, they have mean squared error, mean absolute error, but you can define your own focal loss or whatever loss that you want to include. And if you want to use these for a quick experiment of using these as part of Keras, here are the functions. You can use mean absolute, mean squared, and more importantly, the Huber loss is right here. So go ahead and use that. I hope you found this tutorial to be useful and not too basic. I do these because I get questions from the viewers of my channel, and even if it helps a handful of you guys in filling the gaps in your knowledge, it accomplishes the task. It's worthwhile, I should say. Thank you very much, and please keep asking the questions, and I'll see if I can find a theme in your questions, and if so, I'll do videos like these. Please do not forget to subscribe, guys.